Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 10 of a unit moving charges and magnetism. So let's begin with today's class. In today's session we are going to discuss about two very important topics. First is the torque on the current loop, and then we are going to switch to the magnetic dipole. So let's first start it with the torque on a current loop. Let's have a look that what should be the situation. Let's have a look. This is the north pole, this is the south pole, and as you can see that one of the coil, or we can say a rectangular coil A, B, C, D, has been placed in the uniform magnetic field that has been developed by the this north pole and south pole. So let's begin how the torque would acting. We can say that a rectangular coil ABCD has been placed in uniform magnetic field, and it will going to experience a torque as shown in the figure. Let's suppose I is the current that is flowing through the coil, and each part of the coil experience a one Lorentz force, that are the F1, F2, F3 and F4 respectively, that we have considered. So let's first understood that we first consider that the simple case. Then the rectangular loop is placed in such that uniform magnetic field B is in the plane of the loop. It is in this direction. It is in the plane of the loop. So the field exerts no force on the two arms, that is the AD and BC. Why? Do you have any idea? Why does it have not any magnetic force? Because the force on the current carrying conductor was F is equals to BIL sine theta, where theta is the angle between magnetic field B and length element. This was the force and this was the angle. So when you talk about this branch AD, and when you talk about this branch that is of BC, in this case this theta was 0 degree, and as theta is 0, magnetic force acting on them would be the 0. So force acting on AD would be 0, force acting on BC, even this would be 0. So force acting on AD is 0, force acting on BC is 0, and so that this two are having a 0 force. So it is perpendicular to the arm AB of the loop, and exists a force F1 on it which directed into the plane of the loop. Now let's talk about the other two arms. We are talking about the AB and CD. In that situation the force F1 that is acting on the branch AB, it is the perpendicular. So this theta is equals to 90 degree and this theta equals to 90 degree. Certain force would be there. What it would be, let's look. So magnitude of that force could be considered as B into I into L, while L is the size, and it is the size of the rectangular coil, so it's a BIB. Similarly, let's talk about the CD branch. On CD branch, a force F2 is acting on the arm CD, and F2 is directed out of the plane. It is directed out of the plane of the paper. So that could be written as F2 is equals to BIB. Magnitude wise, this F2 and F1, this both are the same. But direction wise, F2 is acting inside the plane, while F2 that is the force on the CD branch, it is acted outside the plane. So if I consider the net force, this would be the 0. But this is not the case with the torque, because net force is 0. But you can assume that this is F1, this is F2, and if I take this as a midpoint and this is the mg, we can say this. So this is the distance, that is the a by 2, this is the distance, that is a by 2. So there is a torque on the loop due to the pair of the forces, and that pairs are the F1 and F2. So this figure shows that, as you can see, this is going to rotate this loop in this direction. I hope this is understandable. Yes, this is going to move like this. Yes, so as it is going to move in this direction, the torque on the loop can be calculated. The torque would be given as force multiplied by perpendicular distance. If it is going to be rotated from here, So the perpendicular distance will be a by 2, and both the forces, both the torque, are rotating or trying to rotate the coil in the same direction. So I'm going to add torque due to all this. So this torque is equals to F1 into a by 2 plus F2 into a by 2. Let's just replace the value of F1 and F2, which was F1 equals to F2 is equals to BIB. Yes, so it's a BIB into a by 2 plus B by D BIB into a by 2. So if I understood this, it's an A multiplied by B. This is A multiplied by B multiplied by B multiplied by I. This AB, it is something like this. It is something like this. Yes, this was the B, and this as a complete as a A. So this is the area of the rectangular coil. So that could be written as I into A into B, where A is the area of the rectangular coil. Is it clear? Is it clear? Great. So we consider the case when the plane of the loop is not along the magnetic field but makes an angle with it. So first, in this situation, when we consider this was the case that plane of the loop and the loop and magnetic field are on the same angle, that is the theta is equals to 0 degree. Now we are assuming this situation that it is making an angle with it. So if we take the angle between the field and the normal to be angle theta, in the previous case it was pi by 2, because area vector is outside the plane and magnetic field was, we can consider, from north to south. Now the forces on this two branches BC and DA are equal and opposite, and they act along the axis of the coil, which connects the center of the masses of BC and DA. And the forces, this are being collinear along the axis, cancel each other, resulting is the no net force or no net torque. I hope is it clear. This is it clear? Great. So if this is the situation, let's suppose we are talking about the angle theta. So forces on the branch AB and CD are having F1 and F2, and these are all those also the equal and opposite with magnitude, but they are not the collinear forces. It is only the difference that in the BC and DA branch the forces were collinear. Here they are not collinear, and if they are not collinear, I can have a value of this. It's an F1 equals to F2 is equals to BIB, and due to this, as they are not collinear, they are tend to rotate it, and so that rotating effect, that couple, can create a torque on this. So the magnitude of the torque on this loop can be calculated as torque is equals to F1 into a by 2 sine theta plus F2 into a by 2 sine theta. So here torque is less than the earlier case when plane of loop was along the magnetic field, but it is there. So this could be written as torque equals to the net torque is equals to I, which is current flowing through that coil, A, which is the area of the rectangular coil, B, it is the magnetic field, into sine theta. So torque equals to IAB sine theta. So as if we theta tends to 0, the perpendicular distance between the forces of the couple also approaches to 0, and if it is 0, forces are collinear, and so net force and net torque would be 0. So if theta is equals to 0, again torque would be 0. So the torque in the figure can be expressed as vector product of the magnetic moment of the coil and the magnetic field. Here it word comes. The situation was, look at this, torque is equals to I A B sine theta. So we are defining one term, which is the combination of I into A, which we call as a magnetic moment, and this can be represented as, it's a M cross B. Yes, have you remember C is equals to A cross B? When we used to have a cross product, it was A B sine theta. So this torque is equals to M cross B, and this could be written as MB sine theta. So this magnetic moment of the current loop could be given as M is equals to IA. Is it clear? Is it? Yes. And this can be represented as cross product of magnetic moment M and area and magnetic field B. Is it clear? Is it is it clear? Great. So where the direction of the area vector A is given by the right hand thumb rule, this we are talking about the magnetic moment M, and it is directed into the plane of the paper, then as the angle between M and B sine theta can be given as torque equals to M cross B, and the dimensions of magnetic moment we can have, it's an M is equals to I into A. I stands for ampere, area stands for meter square, so that could be written as M0 L2 T0 A1. So this could be written as A into L square, and its unit ampere into meter square. I hope this is clear. So please note down this thing, magnetic moment, this could be written as M is equals to I into A, and this could be vectorically can be written as M is equals to I into A. Yes, direction of this can be given as the right hand thumb rule. Is it clear? Is it clear? Yes, it is a vector quantity that you understand by the arrow itself. I hope this is clear. Is it clear? So first we will do certain practice of the magnetic moment, and then we will come back to this torque equals to M cross B. So let's suppose this is one of the loop. It's a square loop having sides of L by L, and in this current is flowing in this direction. You can see is it is in clockwise direction. So the question is find out magnetic moment associated with the given loop. So as I know magnetic moment is a vector quantity, I must interested in two part. First it's a magnitude, second it's a direction. So let's first discuss with and deal with the magnitude, and then we will move to the direction. So M is equals to I into A, area it's an L square, so this M is equals to I into L square, ampere into meter square. I hope this is clear. Now what about the direction? So for direction, curl your fingers of right hand, curl your fingers of right hand in the direction of current, in the direction of current, then thumb will give thumb will give the direction, of magnetic moment. Yes, so go through it one more time. It says that curl your fingers of right hand, use your right hand and curl your fingers of right hand in the direction of the current, and then the thumb will give the direction of magnetic moment. So here it could be written as M is equals to I into L square, and if I curl my right hand, please use your right hand, everyone, please use it. So curl your right hand in the direction of current, and then you will find that magnetic moment is within the plane, so it's a cross. Yes, is it clear? Is it? Great. So we will continue with this. Let's have one more question. It says that let's suppose it is a circle, and that circle is having radius r, and the current that is flowing like this is I. So it says find out magnetic moment. This is the requirement. They want find out the magnetic moment. So what I'm supposed to do is, it's in first deal with the magnitude. It's a m is equals to I into a. I can see this is circular loop. It's a I into pi r square. And as current is flowing in the clockwise direction, current is flowing in the clockwise direction, again the magnetic momentum would be inside the plane. It's a I into pi r square within that. I hope this is clear. Is it clear? Is it? Will you do one more question here on only? Yes, let's begin. Again, this is a circular loop. Again, this is a circular loop having current I, but at this time current is moving through it in the anti-clockwise direction. So let's just first deal with the magnitude. It's a I multiplied by pi r square. And now the direction. Curl your right hand fingers. Use your right hand fingers. Yes, if you curl your right hand fingers, then the thumb will represents the direction of magnetic moment, which is outside. So as a shortcut, as a short note, what we can understood is that current is if current is clockwise, then magnetic moment is inside the plane. And if current is in the anti-clockwise direction, if current is in the anti-clockwise direction, the magnetic moment is outside the plane. Does it clear? Does it? Are you sure? So will you be able to solve this? Are you sure? Ready for the question? Great. Now let's look at the next question. Find out magnitude of of magnetic moment. So what you are having is, you are having a two coils. One is like this and another it is like this. These two are perpendicular to each other. This two, that means that planes are perpendicular to each other. Let's suppose this is their center, this is the radius r, even this is the radius r, so they are identical coils. And the current through first is like this, current through second it is like this, even current is same. So how could I do this? How could I do this? So deal with one by one coil. Yes, so let's suppose if I took this as a first coil, this as a second coil, then my first coil magnitude could be written as m1 is equals to I into pi r square. M2, that could be written as even I into pi r square. Yes, so I have done up to magnitude. Now it's a turn for the direction. So let's suppose understood that this coil, a first coil, is being placed in a plane. Use your right hand. Use your right hand. Have you used it? You can assume that this has been placed in YZ plane. First coil has been placed in the YZ plane, and assume that it is in YZ plane. Go through the right hand, so that curl the fingers of your right hand in the direction in which current is flowing in the first situation. If you have done it correctly, then your magnetic moment would be in this direction. Your thumb will represent in positive x direction, so this could be written as I cap. I hope this is clear. Is it? Or shall I repeat it? Put your put your coil in the YZ plane. Curl your fingers of the right hand in a direction such as it represents the direction of current, which is in the anti-clockwise direction. Is it clear now? Yes, great. Now curl your right hand fingers and see your thumb, that where does it indicate. If you have done it this correctly, your thumb will represent in the positive x direction, in this direction, positive x. Now it's a turn for the second loop. Put your coil in a plane of an x and y, and curl your right hand finger such that it can represent the direction of current that has been shown in the coil number 2. Have you done it? Where does it indicate? Where does thumb indicate? Yes, it is in the j cap. Very good. So one of the vector is in I cap, another vector is in the j cap. When I find out the mnet, it should be root of m1 square plus m2 square. Yes, magnitude of mnet. So that should be equals to root 2 times of I multiplied by pi r square ampere into meter square. Does it clear? Does it? Are you? Do you got this? Did you get this? Are you sure? Are you? Any issue? Any concern? Is there anything? Is there anything? Are you clear with this? Are you sure? Are you? Any concern? Any issue over it? Is there anything? No. So shall I move ahead? Shall I? Shall I move ahead? Great. So now let's talk about the torque that we were discussing. Yes, we were discussing at this point that this torque can be written as that torque equals to m cross b. Yes, and it is the vector product, of m and b. Is it clear up till now? Is it clear up till now? So let's have certain questions on it, and then we will move to the forward questions. Yes, so first question says that torque acting on the coil is maximum if it is suspended in, first, it's a uniform magnetic field, radial magnetic field, earth's magnetic field, and earth's gravitational field. It would be maximum if it has been radial magnetic field. Why? Because when I say torque equals to m cross b, I mean it's an mb sine theta. And when we are having a radial magnetic field, radial magnetic field, theta would be 90, where max torque could be maximum, that would be equals to mb. So torque acting on it is maximum if you have supplied a radial magnetic field. I hope this is clear. Let's look at next question. It says that the magnetic needle is put in a non-uniform magnetic field. It will experience a force as well as torque. I hope you understand that this is the same situation. If you remember the first unit, if you have remember the first unit, in those case chances, when what we were doing the same thing. We have a dipole has been placed in the uniform electric field, then dipole has been placed in the non-uniform electric field, and then dipole is having a force, then dipole is having a net torque. Even at that time, the torque acting on it was the p cross e. The torque acting on it is the p cross e. Here it's a torque that is of m cross b. So these are the same thing. These are just the correlations between the torque at the magnetic field and the torque at the electric field. So when we used to put a coil that can be represented as a magnetic moment in a uniform magnetic field, it is having a both. In a non-uniform electric field, it is having a both. It is having a force as well as it is having a torque. I hope this is clear. Is it clear? Is it? Great. Now let's move to the next question. The dimensions of magnetic moment, yes, we have already derived it. It's an a into l square. So is it clear? Is it clear? Is there anything that you don't know up till now, or you are having certain doubts? Anything? Anything? Are you sure? Are you sure? Great. So let's move to the questions. Let's suppose magnetic moment of the given coil is given as it's an 4i plus 2j plus 3k, and magnetic field B is equals to 2i minus of 4j Tesla. Yes, this is ampere into meter square. So we have been asked that find out torque acting on the coil. This is the requirement. I need to find out the torque acting on the coil. So I know that torque equals to M cross B. While I say torque equals to M cross B, it should be written as this is I cap, this is J cap, this is K cap. It's a 4, 2 and 3. This is 4, this is 2, this is 3. Cross B, this is 2, this is minus of 4, and this would be the 0. So this could be written as that this is equals to I in a multiplication of, when I used to have a multiplication, we just forget this and this. It's a 2 into 0 0, minus minus plus, it's a plus 12, minus of J, when calculate J, forget this, it's a 4 into 0 0, 2 into 3 6, minus, plus K. K could be written as, it's a 4 into 4, minus of 16, this 2 into 2, minus of 4. I hope this is clear. So this is 12 I cap, minus 6 minus J, it's a plus 6 J, minus 16 minus 4, it's a 20 K in minus. This is the torque acting on the coil. I hope this is clear. Is it clear? Any doubts? Any doubts here? Is there anything? Is there anything? No? Are you sure? Are you? Are you sure enough? Great. Now let's work for the next question. Do it quickly. You are doing good thing. Let's suppose this given situation is shown in the figure, and the figure says it is something like this, that this is X, this has been the Y, and a loop has been placed. Yes, a circular loop has been placed over here, and the magnetic field is something like this in this region. This angle is 45 degree. Magnetic field is something like this. Yes, these are the uniform magnetic field. I hope you understand this. Yes, so the data given is that loop carries a current of 1 ampere. Find out torque acting. Find out torque acting on the loop. This is the requirement. So how will you do it? And the direction of current is given. It is clockwise. So how will you do it? How you are supposed to do this? What do you understand from this? So what I assume is that I am having torque equals to M cross B. So what I need an M, I need a B. Yes. So how could I have M? First thing, that could be written as M is equals to I into A. Yes. So this is I multiplied by, let's assume that this radius is R. So this is I into pi R square. Now what would be the direction of M? What would be the direction of M? As you can see that this is Y and X plane. The loop has been placed in XY plane, and as current is moving, current is flowing through it in clockwise direction. So if current is in clockwise direction, what you need to do is curl your right hand fingers in the direction as current represents. So if you will represent in that direction, then you will find that the thumb is representing in the direction which is inside the plane, which could be said as the minus of K cap. I hope this is clear. It is minus of K cap. So this is M. Now let's turn for the B, magnetic field. So if I divide this into segments, component of this, that it is something like this. This is the horizontal line and this is the magnetic field B. This angle is 45 degree. So this could be written as B cos 45. This could be written as B sine 45. So one is the B cos 45, another is the B cos 45. So magnetic field B could be written as, it's a B cos 45, which is 1 by root 2 I cap, plus B sine 45, it's a B by root 2 into J cap. So now I am having everything. I am having M, I am having B. So what I need to do is, it's a torque equals to M cross B, and that's it. So M cross B, while performing M cross B, it is just the minus of pi r square into K cap. A cross product with, it's a B by root 2 I cap plus B by root 2 J cap. So if I perform this, what I am having is, that it should be is equals to, pi r square B divide by root 2 into bracket I minus of J. Yes, I have performed the cross multiplication and I am having this, it's an I minus of J. Is it clear? Is it clear? What was your answer? Does it have a same? Does it have a same? Does it? Are you sure? Are you? Great. So will you be ready for the next question? Will you be? Are you sure? Let's have a look. This is very important aspect, so please have a look at this very carefully. Let's suppose the situation is given like this. This is X, this is Y, and let's suppose a current loop is there, something like this. A current loop is that, and this would be the direction of M, and initially it is at angle theta 1. So the question says that a current loop of magnetic moment M, or I should say it's a magnetic dipole moment M, is placed in uniform magnetic field B is equals to B naught I cap. So magnetic field is in the X direction. Find out work done required. By magnetic field. Work done required by magnetic field to increase an angle, the angle from theta 1 to theta 2. So how will you do this? This is the direction of magnetic field. This has been given. How could you do this? This is the magnetic momentum, and as it is a current carrying loop, so current must be flowing through it, and M is given, B is given. Even they have mentioned that the angle between this two is the theta 1. So how could I do this? What I need, first thing, I need a work done. How could I have it? I need a work done by rotating it. So what I understood is that torque is acting on this, and that torque can be given as M cross B. And it could be represented as this is M, this is B, so this could be MB sine theta into minus of K cap. I hope this is clear now. Yes. And what I need to do is I need a work done. So I am having one of the option that could be written as dw, that is equals to torque dot d theta, and then I'm going to integrate this. I hope this is clear. it is the same thing what we are supposed to do. It's a work done is equals to force into displacement. So even work done could be written as torque into theta. This is the rough work that has been done, that to be done in your mind. Yes. So even it is the same thing that we have performed at the electric charges and field. At that time we have torque that is of Pe sine theta, and then when we used to rotate the dipole by certain angle theta 1 to theta 2, it is the same thing. So let's perform this. It's a dw which should be is equals to torque dot d theta, and if I integrate this, this is minus of mb sine theta d theta, and this is equals to tw. So let's just integrate this. If I integrate this from theta 1 to theta 2, then this dw will give me a theta. This is equals to minus of mb integration of sine theta. Integration of sine theta would be equals to what it would be. Integration of sine. Integration of sine, it would be a minus of cos theta. From where to where? It's from theta 1 to theta 2. This minus minus positive. So this is equals to mb into bracket cos theta 2 minus of cos theta 1. Even I should write it as this is mb into bracket cos theta final minus cos theta initial. This is the work done by magnetic field. This is the work done by magnetic field. Please do remember this thing. This is the work done by magnetic field, which could be given as mb into bracket cos theta 2 minus cos theta 1. And one more very important aspect is this work done stores in a dipole in a form of potential energy. So this could be even say this could be even, we could say this, that this is the work done required, and this, if we perform this work done, it will stored in a dipole in a form of the potential energy. So this work done is equals to mb cos theta final minus of cos theta initial. This could be written like this. I hope this is clear. Is it clear? Now the situation is, let's discuss this in very detail. The situation is that this is the magnetic field. This is the magnetic field, and as a reference we know that dipole has been put up like this. Yes, dipole, magnetic dipole is being placed like this, and we have that work done is equals to mb cos theta final minus cos theta initial, and we also know that delta u, it's a change in potential energy, could be written as minus of work done. So this could be written as minus of mb into bracket cos theta final minus cos theta initial. I hope this is clear. So if I take theta equals to 90 degree initially, theta initially is equals to 90 degree, then u could be written as, then potential energy or final potential energy could be written as minus of mb into cos theta. Yes, this is u is equals to minus of mb cos theta. I hope this is clear. It is clear, but this is the case if theta initial is equals to 90 degree. If it is not there, we have this relation. I hope this is clear. Is it clear? Is it? So let's just compare this again. Let's just comparison between relations of torque and potential energy of electric field and magnetic field. Let's comparing it. So let's suppose in the electric field torque equals to P E sine theta. It was the case of electric field. This is the magnetic field where torque is used to mb sine theta. Potential energy, or let's say delta U, here here it was minus of P into E into cos theta final minus cos theta initial. Here it is delta U is equals to minus of mb into bracket cos theta final minus cos theta initial. Now if theta initial is considered as a 0, then U should be equals to minus of Pe cos theta. Even here, this is if theta initial is taken as a 0, then delta U would be equals to minus of m into b into cos of theta. Is it clear? So this is the correlation between the electric field and magnetic field. Even you will see many of the things are equal when I compare the electric field and magnetic field. So yes, please do remember these things. Do remember these things. This will help us a lot. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's discuss certain special cases of torque and potential energy together. So let's assume that this is the direction of magnetic field. This is the direction of magnetic field, and my dipole moment, that is the magnetic dipole, has been placed like this. This is the direction of m. Let's assume that this is the direction of m. So if theta is equals to 0, torque, it is the mb sine theta. It is the mb sine theta. And if it is mb sine theta, in reality this m will represent that this is the case. Well, this is the case when direction of m is same. Yes, direction of m is same as the direction of b. So this is torque equals to mb sine theta. If theta is equals to 0, the torque acting on the loop is 0. What about the potential energy? It's a U is equals to minus of mb cos theta. So if cos 0, it's a 1, this is equals to minus of mb. This was the first case. Yes. Second case, let's suppose the situation is something like this. This is the direction of b, and let's suppose this is the direction of m, magnetic moment m. This is the case when theta is equals to 180 degree. Torque, it's an mb sine theta. Again sine 180, it would be a 0, so this is torque equals to 0. And when I discuss the potential energy, it is the case of minus of mb cos theta. So this would be equals to cos 180 is equals to minus of 1, so this is minus plus mb. This was the second case. Let's discuss one more situation where the magnetic field will be something like this, and the dipole moment will be in this direction, such that theta would be equals to 90 degree. So if I compare this, it's a torque equals to mb sine theta, and this is sine 90, which is a maximum values. It's a sine value of 1, so this is the maximum torque that could be written as torque is equals to mb. Let's talk about the potential energy. This is a minus of mb cos theta, and this is cos 90. So when it's a cos 90, this potential energy would be 0. So now, do you remember that we have a certain stable equilibrium and unstable equilibrium? Have you remember it? That we have a certain stages where we could say that your system is in stable equilibrium. At certain stages we used to say that it is in unstable equilibrium. Have you remember it? Yes. it is always the case that potential energy of your system when potential energy of your system is maximum, look at this, it's a minus of mb, it's a plus of mb. So this is the maximum potential energy, this is the minimum potential energy, and state of maximum potential energy is always unstable equilibrium. I hope this is clear. When potential energy is maximum, when potential energy is maximum, it is the state of unstable equilibrium. And when potential energy is minimum, when potential energy is minimum, it is the case of stable equilibrium. Does it clear? Does it? I hope this is clear. Is it clear? So u minimum, it's a stable equilibrium, and u maximum, it's a unstable equilibrium, sorry. So when m and b is having an angle theta which is equals to 0 degree, it represents state of stable equilibrium. When angle between m and b is 180 degree, it represents state of unstable equilibrium. I hope this is clear. Is it clear? Is it? Great. So please do remember this and have a question based on this. Find out work done required by magnetic field. Find out work done required by magnetic field to rotate current carrying coil from unstable equilibrium to stable equilibrium. So what do we require? We required work done to rotate it. Work done required by magnetic field to rotate the current carrying coil from unstable equilibrium to stable equilibrium. So how should I do this? What I need to do is, this is work done, that should be is equals to mb into bracket cos theta final minus cos theta initial. I hope this is clear. So this is cos theta final minus cos theta initial. Should I rewrite? One second. Yes, this is cos theta final minus cos theta initial. So finally I should be at stable equilibrium, and when stable equilibrium the theta will be 0, so it's a mb into cos of 0 degree minus this is the theta initial position. Initially we should be at unstable equilibrium, so one for unstable equilibrium it is the cos 180 degree. So this is mb into bracket cos 0 degree, it is 1, minus of cos 180 degree, it's a minus of 1. So this is 1 minus of 1, this would be 2, so this would be 2 mb. This is the work done required. This is the work done required. I hope this is clear. Is it? Are you sure? Are you sure? Can it be done by you? Can it be? Yes? Great. Ready for the next question? You are doing pretty good, pretty good. Well done. Keep it, continue. Ready for the next? Let's have a look. If work done require to rotate coil by an angle of 30 degree, if work done required to rotate a coil by an angle of 30 degree is 80 joule, find out torque acting on it at that instant. find out torque acting on it at that instant. This is the requirement. So how will you do it? What I know is that I understand that my torque is equals to mb sine theta, and my potential energy or work done stored, it's minus of m into b into cos theta. So if I take a ratio of this, if I take a ratio of this, what I can have is that this has been, and mb could be gone, this has gone, this has gone. So torque divided by potential energy would be, this is sine theta, this is cos theta, so this could be minus of tan theta. Torque is required, potential energy is given, it's an 80, this is equals to minus of 1030 degree. What is the value of 1030? What does it? 1030, yes, yes, 1 by root 3, great. So torque equals to minus of 80 into 1 by root 3 Newton into meter. Does it clear? Does it? So will you be comfortable with this? Will you? Yes, yes, are you sure? So can we switch to the one of the new concepts? Yes, let's have a look. It says that we are now looking for the magnetic dipole moment of revolving electron. So let's look, what does it says? It's a magnetic moment of a revolving electron. So we are going to discuss a certain thing which is associated with chemistry as well. Yes, so let's look, it's a Bohr's atomic model picture. In the Bohr's atomic model picture, the electron to revolve around a stationary but heavy nucleus of charge that we assume as a Z into E. Yes, so the moving electron, electron is rotating around the stationary charge, and if it is rotating, it can create a current, and that current will be equals to E by T. This is the same thing, this is nothing new for us. It's a I is equals to Q by T. We used to have this. Yes, we used to have this I is equals to Q by T. So we are doing the same thing. It's an I is equals to E by T, where E is the charge of the electron, T is the time period of revolution, and let's suppose that V is the orbital velocity, V is the orbital velocity, and R is the radius of its orbit. So can we say T is equals to 2 pi r by V? And if I replace the value of T from this, I can have this, it's an I is equals to E into V divided by 2 pi r. This I could be written as E into V divided by 2 pi r. So if I have written this, I equals to E into V divided by 2 pi r, we can find out one more thing. It's a small magnetic moment that I have represented here as a mu L. Yes, even that can be represented as M, associated with this revolving electron, because it is revolving. So this magnetic moment could be written as I into pi r square. Basically it was I into a M is equals to I into a, and it is revolving in a circular path having a radius of r. So let's just replace the value of I. It is EV pi r square divided by 2 pi r, the complete. So if I solve this, the pi has cancelled here, r would be having 1 power, it is having 2 power. So the term I have been left is the EVR by 2. This is magnetic moment. Let's just multiply and divide. It with the mass of an electron. So what I am having is, let's observe this very carefully. This is mass, this is velocity, and this is the distance. It's a perpendicular distance. So mvr, and mvr could be written as L, which is the angular momentum of the electron about the nucleus. So this is m, this is L, and that could be written as m by L is equals to E by 2 into m. Here it's a mass of an electron. So this is m by L is equals to E by 2m. So m by L, always remember this have a very good applications. So m by L, that could be written as E by 2m. If we represent this according to the vectors, it would be an m by l is equals to minus of e by 2m. One more thing, that the negative sign shows that angular momentum L and magnetic momentum M are opposite to each other. That means, that means angle between angle between M and L is 180 degree pi. Please do remember this. This has been asked once in the AIMS examination, that what should be the angle between M and L. Yes, please do remember this. So this is the property, helps to explain the magnetic properties of the material. And beside this orbital magnetic moment, electrons will also having, and it is having a spin magnetic moment that you might study it into your chemistry classes. But does it clear? What physics require is, it's an m by l that should be is equals to q by 2m. It's a charge divided by 2m. Second thing, angle between m and l, angle between m and l is 180 degree. It's a pi. Is it clear? Is it clear? So please note it down, please note it down, all these points, and we will be moving towards the applications of this. Yes, so are you ready? Are you ready with this? Let's have a one of the question. It says that in a magnetic dipole moment of a revolving electron, the time period, it's a t is equals to 2 pi r by v. That's it. This is the answer. You got it. Great. Is it clear? Is it clear? So ready for the question? Let's have a look. The question says that a disk of mass m, a disk of mass m, radius r, and charge q, is rotating with angular speed omega, about an axis passing through its center, and perpendicular to the plane. Calculate its magnetic moment so go through this, take 30 seconds of your time, and let me know what you are planning to do. What can you do? Got it? Any idea? If you are thinking that, that sir, I will do this, it's a m is equals to q into v into r by 2 that you have derived in the previous slides, then this is the incorrect one. You could not do this. Why? Because this is the disk, and disk, while disk rotates, you have studied the rotational motion in the class 11. In those times you have been studied that every object requires a certain inertia. Yes, every object is having certain inertia while rotating, that we call as a moment of inertia. Yes, Here there is nothing like moment of inertia, so it means that according to this every object requires the same amount of force or same amount of torque to make it rotate. But this is not true, because every object has different inertia, and when every object has different inertia, every object must be applied with certain different forces, and that forces will help us. I hope this is clear. Is it clear? So we cannot do this thing. Yes, this is the incorrect approach. We cannot go with this. I hope this is clear. Is it clear? So we cannot go with this. Now what next? What next? What can I do? So I have one more approach. Let's have a look. Let's have a look. It is the m by l should be is equals to this m by l should be is equals to q by 2m. Yes, and from this this m could be replaced by q by 2m multiplied by l. Is it clear? Is it? So this could be written as q by 2m multiplied by l, and that l could be represented as I omega, where I is the moment of inertia. I hope this is clear. Is it clear? So when I write the magnetic moment, when I write it's a q by 2m multiplied by I into omega. It was the disk, and for disk I could be written as mr square by 2 multiplied by omega. This m has gone, and when this 2 has gone, it would be the q omega r square divided by 4. This is the magnetic moment that have been associated with a disk of mass m. I hope this is clear. Is it clear? Is it? Are you sure? Can it be done? Can it be done? Would you like to go for one more question so that this practice will be rich to the subconscious minds? Yes? Will you be? Let's have a look. That question and the previous question. If disk has been replaced by solid sphere, if disk has been replaced by solid sphere of same dimensions, find out magnetic dipole moment. You need to find out magnetic dipole moment. How will you do this? How could you? So what I supposed to do is it's an m by l, that would be q by 2m, and while doing this I am having m is equals to q by 2m multiplied by I into omega. At this point of time it is the solid sphere, so it's a moment of inertia of solid sphere, which would be 2 by 5 mr square multiplied by omega. So this m and m could be cancelled, this 2 can be cancelled. So if this is going to be cancelled, this could be written as m should be equals to it's a q into omega into r square divided by 5. This is the magnetic moment. I hope this is clear. Is it clear? Is it clear? Are you sure? So so can you do this kind of questions? Are you sure? Are you sure? Can it be done? Great. So can we move to the different type of question based on the same application? Can we? Let's have a look. So if the question says that for a atomic model of hydrogen, for atomic model of hydrogen, if radius is r, speed is v. Depends on principal quantum number n. Principal quantum number n. Then set up relation between magnetic field B, magnetic field B, and and quantum number n. Do this. Do this. So what do they require? They require that atomic model of, let's suppose hydrogen is given. So first thing, what is the atomic model of hydrogen atom? So it says that let's suppose a circular path would be there. At a center, at a center part, nucleus would be there. Hydrogen, a proton would be there, and electron was there, which is keep rotating on the same path, and the radius is r, and it is moving with velocity v. So it is the atomic model of hydrogen atom, and if it depends on the principal quantum number n, then we need to set up relation between magnetic field and quantum number n. So how should I do this? First thing, when and when any charge particle is rotating, when and when any charge particle is rotating in a circle, I am having a magnetic field at its center, which could be relate as B is equals to mu naught I by 2r multiplied by theta by 2 pi. Have you remember this? Yes, it is from the Biot-Savart law. We have derived this. It's a mu naught I by 2r into theta by 2 pi. Here theta, it's a complete circle, so this could be written as mu naught I by 2r. This is the magnetic field. Here the current has been developed by this E, so this could be written as B is equals to mu naught I by 2r. This is mu naught by 2r multiplied by I could be given as it's a q by t, and when I write the t, it's a mu naught by 2r multiplied by q into t could be written as 2 pi r by v. Yes, we have recently used all these relations. So this is mu naught into q divided by 2 into 2 pi, it's a 4 pi multiplied by v by r square. This is the magnetic field. So if you observe these terms, these are the constant, this all are the constant terms. So, and velocity and radius depends on the quantum number that you have learned in the chemistry. Even you are going to study about this in the modern physics. So this B could be represented as V by R square. This B could be represented as V by R square. So V, it's directly proportional to the 1 by n that you have derived over here in chemistry, and this radius is directly proportional to the n square. So let's just put it up. It's a B that is equals to 1 by n, and this r square, this is equals to 1 by n to the power 4. This is n1, this is n4, so this could be written as 1 by n to the power 5. This is the relation between magnetic field while electron is rotating around a centrally charged particle, which we call as a nucleus. Yes, and due to its rotation a certain magnetic field has been developed, and that magnetic field depends on the quantum number n, and this is the relation. B is directly proportional to the 1 by n to the power 5. This is very effective question. Yes, because when this question has been asked, a student always thinks that this is the question related with the modern physics, and in modern physics you are not going to find anywhere magnetic field. So time is going to be wasted and question is not going to be done. Yes, please do remember this. This is very beautiful question. I hope this is clear. Is it clear? Is it clear? Is it? Yes. One more informative question. Let's have a look. Do you remember Bohr's magneton? Do you? Do you know about the Bohr's magneton? We are not going to discuss what it is, but theoretically, but we are just going to prove it, and you just remember the value of it. What is Bohr's magneton? Let's look at that. We understood that it is m by l, that should be is equals to q by 2m. Is it clear? Yes. So it is m is equals to q by 2m, or I should say it's an a by 2m multiplied by l, and this l could be represented by it's an n into h by 2 pi. How now? Why? How this has been arrived? Yes, this is postulate 2. It's a postulate 2 from Bohr. I hope if you have remember this, that all the electrons will rotate around it in a certain orbital state only, and angular momentum of that state will be equals to integral multiple of h by 2 pi. Yes, you have not tuned in to the lecture of chemistry. This is just the physics. Yes, so it is basically a science, and every science has been linked everywhere. So this is let's suppose what you need to do, what Bohr's magneton is, just keep n aside, it's a quantum number aside, and remaining all would be put in one of the box, that is equals to E into h divided by 2 2s are 4 into pi into m. Is it clear? So this box could be represented as mu b, and this is Bohr's magneton. I hope this is clear. Is it clear? Is it? Now do you have any doubts? Do you have any doubts over this? Is there anything? Is there anything? Are you sure? Are you sure? Are you? Are you sure? Great. So let's just wind it up this session over here. This was very interesting session. I love it. So please do the questions based on this. Please have as many practice as possible, because these are the very small topics, small applications, but they have a very high impact when we consider them for the competitive examinations point of view. Yes, so please do as many questions as possible, do it regularly, do one thing, because this is a very big unit. It's a moving charge and magnetism. We have started it with magnetic field, and then now we are on just the verge of completion of this. So please revise it thoroughly, from magnetic field to the Biot-Savart law, and then from Ampere-Circuital law, and so on. Please revise it. This will help us. Thank you. Have a good day. Take care. Bye bye.